Let's talk about lattice topic. To understand lattice, you should understand minimal, maximal, minimum, maximum elements. Let me discuss with minimal element first. To understand minimal element, first you should know what is S, what is P, what is P less than or equal to. So we define these are all elements minimal, maximal, minimum, maximum only for partial order relations. Okay, and already we know that we use hash diagrams only for partial order relations. Okay, that's why the basic point is this relation is partial order relation. That's why we denote it by P. Sometimes I write poset. That means poset is a set which is a partial order relation. Okay, it's a group like this is poset. So a set comma a partial order relation is called poset. Now this less than or equal to is just symbol. Okay, need not be mathematical operator, that relational operator. Okay, so we use this symbol to represent one of the partial order relation. Remember it. So yeah, I have a partial order set and a partial order relation. Then there is one subset called S, which is subset are equal to P. These are all the details of S comma P comma less than or equal to. In such scenario, minimal element of set S I am going to define. Minimal element of set S is like this. I am writing it. So X. X is called minimal element, let's say. Then let me write it. X belongs to S is called minimal element. Minimal element. Before completing the definition, I'll explain you the concept of that minimal element. Minimal element should be an element, so which is, I can say there is no element which is related to that element in the set S. So whenever I say X is minimal element, then there is no element in S which is less than or equal to X. Less than or equal to means relation. That means there is no element related to X. Let me write it. Minimal element, then there is no other Y. There is no Y such that, what kind of Y does not exist? Such that Y is related to X. Other than, remember one thing, Y is not X. If Y equal to X, then definitely every element is related to itself. Why? Because this is a partial order relation, isn't it? In partial order relation, definitely reflexive property holds good and every element will be related to itself. Other than that element itself, there is no other element which is related to X. Then we say X is minimal. Okay. So let's use this definition and try to understand minimal element in this example. Let me fix the set first. Okay, let's say set here is 1 comma 2 comma 3. In this 1 comma 2 comma 3, which is S, here P is nothing but 1 2 3 4 5 6, and partial order relation we don't know, like maybe divides, anything we don't know, but we have the relationships. When you have relationships, you don't require to know the name of the symbol or name of the relation, right? Divides, otherwise less than or equal to, these are all the names of the relations. When you got the relation itself, then the name of the relation doesn't matter. We have relationship now, you see. So 1 cannot be minimal in 1 2 3. The reason, if 1 is minimal, there should not be any Y which is related to X. But here 2 is related to 1, isn't it? 2 is related to 1. 3 is also related to 1. That's why we don't say that 1 is minimal. But whereas 2 is minimal because there is no Y which is related to 2. Similarly for 3 there is no Y which is related to 3, isn't it? That's why definitely 2 comma 3 are minimal, right? Answer is 2 comma 3 minimals. Okay, so minimal is 2 comma 3. We'll go to next question. Otherwise we'll see here on 4 5 6. Okay, on 4 5 6 what is minimal? So definitely 6 is not minimal because there is some element 4 which is related to 6. But don't check this one. Don't say that 1 is also related to 6. Of course, if 1 is related to 6, it doesn't matter. According to the definition, we should show one element which is related to 6, which belongs to our set. That means this Y should belongs to S. Let me add it. There is no Y belongs to S. Understand? So that's why whenever to say that 6 is not minimal, you should show evidences from this 4 5 6. Okay, in 4 5 6, is there any element which is related to 6 and not equal to 6? Yes, that is 1 is 4, 1 is 5. That's why 6 is not minimal. Okay, if really 6 is minimal or any element is minimal, you never get that kind of evidence. What is that evidence? Which is y, which is belongs to s, and it is not equal to x, but it is related to x. Okay, and a related element which is not itself and it belongs to s. Okay, so we'll see one more example of minimal elements for this problem. Let's take this problem. In this problem, let me calculate minimal element for in this problem 4 5 6. Already we know that, that's why 4 and 5 are minimal, isn't it? 4 5, because there is no element related to 4. So you might think that 1 is related to 4, but 1 should belongs to our set 4 5 6. That's why in this 4 5 6 there is no element which belongs to 4 5 6 which is related to 4. Similarly, there is no element related to 5 in this 4 5 6. That's why 4 comma 5 are minimal. Come to this one. In this one, let's say 1 2 3. In 1 2 3, minimal is 2 and 3, isn't it? Because there is no element related to 2, there is no element related to 3 in this 1 to 3. Okay, that is what. Let me point out that this is 6. Okay, now second one, what about 4 5 6? In 4 5 6, minimal is 4 and 5. The reason, 4 is, there is no element related to 4, correct? And I am calculating minimal elements. Second one is, there is no element related to 5. Yes, but 6 is not minimal because 4 is related to 6, 5 is related to 6. Understand? Now we'll take one more example. In 2 4 5 6, let me take 2 4 5 6. In this 2 4 5 6, what is minimal? Is there any element related to 2? No, right? Don't say 1, because whatever the answer you give, that should belongs to 2 4 5 6. In 2 4 5 6, there is no element which is related to 2 4 5 6. So 2 will become minimal. So what about 4? No, 2 is related to 4, which belongs to our set. That's why 4 is not minimal. Cancel it. Similarly, 5 is not minimal because evidence is 2. 2 is related to 5. 6 is not minimal because 2 is related to 6. How can you say that 2 is related to 6? Did you remember? According to partial order relation, when you have an edge from 2 to 4 and 4 to 6, there was an edge called transitive edge. We removed it, right? But still relation holds. Though we don't have edge, but it was there initially, right? 2 to 6, which was transitive edge. Even that indicates that there is a relation between 2 to 6. Otherwise, recall transitive property. Every partial order relation is transitive. That means when there is a relation from 2 to 4, 4 to 6, definitely there will be relation from 2 to 6, isn't it? That's why 6 is not minimal, because there are a lot of elements which are related to 6. Okay, in that way, so you can understand minimal element. Okay, let's see maximal element of set S. Maximal element of set S is defined like this. X belongs to S. First of all, that element again should belongs to S, is called maximal element of set S. If there is no Y, see, which is belongs to S, such that X is related to Y. So whenever you want to say that X is maximal, right? Okay, let me pictorially show what happens when X is maximal. This is your set S. Okay, so in this set S, when X is maximal, there is no Y in S, which is of course X not equal to Y. Remember, other than X, there is no Y, so that X is related to Y. That means you never see this kind of evidence where there is some element Y, so that there is a path from X to Y. Okay, if it happens, then that X cannot be maximal. Okay, so I am showing you again. If X is this one and there is a path from X to Y, it's a path, need not be a direct edge. Whenever there is a path like this, then X cannot be maximal. So simple. Okay, but necessary condition is Y is not X. Second one, Y should be part of S. Okay, don't show an element from outside of S. Let's see the same thing here. Let's take set S as 1 2 3. In this 1 2 3, what is maximal? Definitely 1 is not maximal, because I can show you an element called 2 where 1 is related to 2. That means whenever 1 is related to 2, where 1 and 2 belongs to same set, 1 is not maximal. Next, why? What about 2? Yeah, there is an element called 4. Of course, there is a path from 2 to 4. It doesn't mean that 2 is not maximal. The reason you should show an element, did you remember? Y should come from S. Is there any Y? Because our set is 1 2 3. Is there any Y which is, where 2 is related to that Y? Show me an element Y where 2 is related to Y, where Y also belongs to 1 2 3. No, such element does not exist, because of course 2 is related to 4, but 4 is not part of 1 2 3. That's why 2 is maximal. 2 has this kind of structure. There is no element related to 2. There is no element related to 3 in 1 to 3 other than 3, right? That is what definition says. That's why 3 will become maximal. Yes, you can have multiple maximal elements. In this problem, answer is 2 comma 3. Okay, now take this example. Maximal elements of, let's say, A B C D. A B C D. We'll try to calculate maximal element. Since A is related to B, right, then definitely A cannot be maximal. Let me cancel some of the non-possibilities. So definitely A cannot be maximal, because when there is a relation from A to B, which is part of again S, right? This is S, B is part of S. That's why A is not maximal. What about C? A is related to C, then A is not maximal. So what about C? Is it maximal? No. There is a relation from C to D. Still D is part of your set. Then C cannot be maximal. So B cannot be maximal because there is a path from B to D. So such path should not exist. Okay. For D, there is no such path from D to anything else. That's why. So don't show that D is related to D, and don't say that there is a path from D to D. Of course I know that, but in condition, the element whatever you show and there is a path, whenever you show it, that element should not be equal to the concerned element we are talking about. To say that D is maximal, so you can have, still you can, to say that D is not maximal, you should show the different element. That is what I want to say. So don't show this kind of evidence. Okay, and don't say that D is related to D. How D is maximal? In the example definition, clearly I said that your example of Y, that means there is no Y which is not equal to X. You are showing Y which is equal to X. Okay, don't show that. So that's why still D is maximal. Take this example, 6 7 8 9 10 11. Maximal elements of, let's say, 6 7 8, and let's take 9. In 6 7 8 9, maximal elements are, first of all, let's cancel out some of the non options, like which are not correct. 6 is not maximal because 6 to 7 there is a relation. 7 is not maximal because 7 to 9 there is a relation. 8 is not maximal because there is a relation from 8 to 9. Then only possibility 9. Let's clearly check. Yes, there is no Y on top of 9. Understand? So that there is a path. So 9 is maximal. Okay. Now we'll take one more example. 7 8 and 9 10. In 7 8 9 10, again same story. 7 8 9 10. 7 is not maximal because there is a path from 7 to 9. So 8 is not maximal because there is a path from 8 to 10. You see, 8 to 10, right? Okay, 9 and 10. Since there is no path from 9 to 10, okay, don't say that this is a path. Okay, why it is not a path? Here the intention of path is relation, right? So 9 to 10 there is no relation. We have a relation from 8 to 9. Directions are important. Okay, so never take this kind of downward path, 9 to 8, since we know that it is a partial order relation and 8 is related to 9. Okay, but not 9 is related to 8, isn't it? When 9 is not related to 8, you can't say that 9 to 8 there is a edge. Okay, it is an edge from 8 to 9. Directions are important. Okay, so that's why you can't take path like 9 to 8 followed by 8 to 10. We have only path from 8 to 10, not from 9 to 8. So that's why there is no path from 9 to 10. Now, when there is no path from 9 to 10, then there is no element you see which is on top of 9. That means from 9 there is no relation to any other element of 7, 8, 9, 10. There is no relation from 10 to any other element of 9, 7, 8, 9, 10. That's why 9 and 10 are definitely maximal. Okay, answer is 9 and 10. Let me mark it. So this is about maximal elements. Now let's define minimum element of set S. An element X belongs to S is called minimum. This is different from minimal. How it is different, we'll see. If for every Y belongs to S, X is related to Y. That means this is your set S, let's say. Okay. So these are all elements like X1, X2, X3, whatever. And you have X2. Okay, so on. Now whenever you want to say that X is minimal, what should happen is all other elements of your same set Y, that means now X1 is X1, X2, X3, these are all elements should be, such a way that this X should be related to them. That means X2, X1 there should be a path, X2, X2 there should be a path, X2, X3 there is a path. In that way, for every other element you should show a path. Okay, then we say that element is minimum. So how can we imagine minimum element in hash diagram is, so you will see X like this and all other elements of your same set S, I am talking about S, all other elements of your set S, let's say, will be, you can imagine them like this. Okay, element 1, element 2, element 3, element 4, element 5. See, there is a path from X to A1, X to E2, X to E3, X to E4, X to E5, of course X to X. That's why there is a path from X to every element of Y. If you show that, then automatically that element X will become minimal. Okay, sorry, minimum. So minimum is different from minimal. Okay, minimal's idea is there is no element which is related to, so whenever X is minimal, there is no element. We are talking about a single element. There is no element Y which is related to X. Okay, if this kind of element does not exist, X becomes minimal, but minimum concept is different. We'll see example. Let's take this picture. 1, 2, 3, 4, 5, 6. Let me fix a set as 1, 2, 3, 4. In this 1, 2, 3, 4, what is minimum? So minimum element is an element which is related to every other element. See now, my guess is 1 is minimum. I will prove it. 1 is related to 1, obvious, reflexive property. 1 is related to 2, according to the diagram, right? So 1 is related to 3, absolutely right. 1 is related to 4, yes, there is a path, transitive property. In that way, 1 is related to every element, that's why 1 is minimum. Now let's try 2. If really 2 is minimum element, 2 should be related to 1, 2 is related to 2, 2 is related to 3, 2 is related to 4. This is what should happen. 2 is related to 1 is absolutely wrong. Otherwise, this is correct. Maybe 2 is related to 3 is wrong because there is no path from 2 to 3. Okay. Always path should go from down to up, right? Like this. So using these edges, we cannot get a path from 2 to 3. That's why. So, but 2 to 4 there is a path. Finally, whatever may be the reason, 2 is not minimum element. Similarly, 3 is not minimum because 3 to 2 there is no path. Now 4 is not minimum because from lot of element there is no path to 4. Understand? So finally 1 is the only minimum element. One more important observation is in any given set you can't have multiple minimum elements. I will tell you the reason. Why there cannot be two minimum elements E1, E2 at a time. According to the definition of minimum element, example, if E1 is minimum and E2 is also minimum, if they belongs to same set S, right? Okay, what's the definition of minimum? Minimum should be less than or equal to every element of set S. Since E2 is also a part of set S, then E1 should be related to E2, isn't it? Let me write it. Note down the point number 1. Second one. If E2 is minimum element, then E2 is also related to E1, right? Point number 2. Because minimum element should be related to every other element of the set S. Then according to partial order relation, since partial order is antisymmetric, E1 is related to E2, E2 is related to E1 is only possible in one case, that is E1 equal to E2. Please recall antisymmetric property, correct? So that's why. So here you can't have multiple minimum elements, remember. Now answer is only one. Let's go to one more picture, this one. In this one we will try to calculate minimum element. Let's take 1, 2, 3, 10. 1, 2, 3, 10. 1, 2, 3, 10. So what is minimum element? Can I say 1 is minimum? Yes. The reason 1 is less than or equal to 1, that means less than or equal to means relation. Okay. 1 is related to 1, 1 is related to 2, yes. 1 is related to 3, there is a path. 1 is related to 10, absolutely. So that means what? 1 is minimum. So you can cross check like 2, 3, 10 cannot be related to every other element. 2 is not related to 1, 3 is not related to 1, 10 is also not related to 1. That's why they cannot be minimum elements. Okay. We will see one more example in this problem. Let's take 1, 2, 3. Let's take 3, 7, 10. 3, 7, 10 and 2. 3, 7, 10, 2. So definitely 10 cannot be minimum, 7 cannot be minimum because 10 is not related to 3 and 7 is not related to 3. Minimum element should be related to every element, isn't it? That's why only possibility we have is 2 and 3. 2 is related to 2, absolutely right. 2 is related to 3, absolutely wrong. That's why 2 cannot be minimum. Similarly, 3 is supposed to be related to 3, 3 is supposed to be related to 7, 3 is supposed to be related to 10 and 3 is related to 2. Then only I can say that 3 is minimum. So now let's say it is right, 3 less than or equal to 7, right? Less than or equal to means relation. Remember one thing, R and less than or equal to are same, represent same symbol. R means relation, less than or equal to also relation, not mathematical operator. Remember it, okay? This is not mathematical comparison. This is just symbol for R, okay? Now 3 less than or equal to 10, right? Don't use mathematics, see the picture and tell me. 3 less than or equal to 10, right? 3 less than or equal to 2, no, there is no path, right? That's why wrong. Since 3 is not related to 2, so 3 cannot be, minimum element. In that way we can check that there is no minimum element in this group 3, 7, 10, 2. Understand? Let's see maximum element. An element is called maximum element which belongs to S if for every y belongs to S, that means for every element of that set S which we are talking about, y should be related to x. To say that x is maximum among a set S, this is your set S, then every element should be related to x and that every other element should be, which we are talking about is every other element is a member of S, okay, that is enough. So there may be some other elements like which are not members of S, like x or y is A. If this is not related to x, doesn't matter. What is important? Every element of your set S should be related to x, then x will become maximum. Whenever you have maximum element, it will have this kind of structure like this. So it will be on top of the all other elements and they are all related to x. Let's see with examples. First we begin with this one. What is that? 1, 2, 3, 4. In 1, 2, 3, 4, what is maximum? I guess 4 is maximum. The reason, it satisfies the definition. You see, we have to prove that 1 is less than or equal to 4, 2 is less than or equal to 4, 3 is less than or equal to 4, 4 is less than or equal to 4, isn't it? So that's obvious. Here less than or equal to means relation. Please remember, okay, related. Yeah, 1 is related to 2, correct. 1 is related to 4, yes. 2 is related to 4, correct. 3 is related to 4, yes. 4 is related to 4, absolutely, because reflexive property, every element is related to itself. That's why 4 is having the property of maximum element. That's why 4 is maximum. In this set, no other elements will have same condition. You can check it, okay. Now second one, let's take 3, 4, 5. In 3, 4, 5, what is maximum? I guess 4 first, okay. So 4 is maximum, then 3 should be related to 4, 4 should be related to 4, 5 should be related to 4. Okay, so 3 is related to 4, absolutely right, because there is a path from 3 to 4. 4 is related to 4, correct. 5 is related to 4 is absolutely wrong, because there is no path from 5 to 4. Yes or no? Don't say that 5 to 3, 3 to 4. Directions are important, we know that, correct? In relations, when A is related to B, we can't say B is also related to A, isn't it? That's why here we know that using the picture, 3 is related to 5, but not 5 is related to 3. That's why going from 5 to 4 is absolutely impossible. Let's come to the next picture. 1, 2, 3, 7, 9, 10. Let's take 1, 2, 3, 7 first. What is maximum on 1, 2, 3, 7? I guess 7 is maximum because 1 is related to, let me take relation, 1 is related to 7, 2 is related to 7, 3 is related to 7, 7 is related to 7. This is what the definition. Every element should be related to some element. Then that some element will become maximum. So 1 is related to 7, everything will cross check. 1 is related to 7, yes, there is a path. 2 to 7, yes, path. 3 to 7, there is a path. 7 to 7, there is a path. Absolutely 7 is maximum. Let's check one more example. 2, 3, 7 comma 10. Okay. In 2, 3, 7, 10. Let's guess that 7 is maximum. If 7 is maximum, what is the definition of maximum element? So 7 should be, every other element should be related to 7. 2 is related to 7, 3 is related to 7, 7 is related to 7, 10 is related to 7. That is what we have to prove. 2 is related to 7, absolutely right. 3 is related to 7, absolutely right. 7 to 7, obvious. 10 to 7, there is no path from 10 to 7, it's wrong. In the same way, there is no path from 7 to 10, there is no path from 10 to 7, then neither of them can be maximum, right? So you can, if you apply 10 in the place of 7, you get problem here, correct? So where 7 related to 10 is absolutely wrong. So 10 also cannot be maximum. Neither 7 is maximum nor 10 is maximum. So similarly, we can prove that 2 and 3 also not maximum. So what is maximum here then? There is no element which is maximum. Yes, it is possible. Sometimes you may not see any maximum element, you may not see any minimum element. It is not compulsory. But definitely you will see at least one minimal element if there is at least one element in the set. You can see at least one minimal element, at least one maximal element if your set which you are talking about is non-empty. But whatever the big set you take, minimum and maximum elements might not exist sometimes. Okay, so this is about minimal, maximal, minimum and maximum elements. Let's talk about upper bounds and lower bounds of a set S. So upper bound of any set S is a set of elements, and any element of that upper bound, okay, that should belongs to your poset P, and it should satisfy one more condition. Okay, whenever I say X is a member of upper bounds of set S, then that X should belongs to poset. And second thing, for every Y belongs to your set S, so for which you are calculating upper bound, Y should be related to X. That means this is, let's say, your set S. Okay, so this is your set S. Elements are, let's say, X1. Let me take Y1, Y2, Y3, so on. Okay. Now, whenever I want to say X is an upper bound of set S, X should belongs to a poset. Okay, this is your poset, let's say, this time. Okay, X can be anywhere which belongs to your poset. Such a way that every Y which belongs to your set S, that means this is Y, should be related to X. See, less than or equal to means relation here, R. So Y1 is related to X, Y2 is related to X, Y3 is related to X, so on. So this is the structure of upper bound. How it is different from minimum element? Minimum element, generally minimum element is an element which belongs to your set S, but upper bound need not to be, an element of your set. X can be anywhere, but the property of X is like minimum element. So every other element is related to X. So that's the reason there can be multiple upper bounds for any set S. Example, if X is related to some element called A, okay, Since already we know that y1 less than or equal to x, y2 less than or equal to x, y3 less than or equal to x, y4 less than or equal to x, and already I am saying that now x is less than or equal to a. In this scenario, according to transitive property, so here less than or equal to means relation. Okay, let's read it. Y1 related to x, x is related to a, then y1 definitely will be related to a. Similarly, y2, y3, y4, everything will be related to a. That is what the definition of upper bound. So a also would become upper bound. Understand my point? So from now onwards, whenever you say something is an upper bound, and if you see another element directly or another element which is connected to x, that would become upper bound. Okay, in that way you can extend upper bounds to any length, like a, b, c, all are upper bounds, even x. So this is the concept of upper bound. Now we'll see what is lower bound. Okay, before that let me take one example and explain you what is upper bound. After that we'll come to lower bound. Let's say take this picture, and I would like to talk about upper bounds of a comma b comma c. Okay, so this is what our problem. This is your set S. Whenever something is upper bound of set S, a, b, c, then that element should be any element out of this poset. Okay, so answer might be a, b, c, e, d, f, g, but the only thing is that element should be related to all these elements. Like a is related to this. Tell me one element which is related to a, b, c, then that will become upper bound of a, b, c. I think e is the wrong answer, right? We'll see why E is not upper bound, because yeah, A is connected to E, correct? That means A is related to E. Now B is related to E. B is related to E, absolutely right. What about C? C is not related to E. There is no path from C to E, correct? So that's why E is not upper bound. So with this concept, I think G is the upper bound of A, B, C. Now you see, I can prove that A is related to G, correct? B is related to G, correct? C is related to G. That means related, right? So path and relation are interchangeable. So finally you understand that G is the upper bound of ABC, correct? So I think for ABC there is only one upper bound. Sometimes you might get multiple upper bounds. I'll show one more example. Example, let's say B comma D. Okay, upper bound of B comma D. I think E is an upper bound because B is related to E, D is related to E. That's why E is an upper bound. Whenever E is connected to G, G also would become upper bound. The reason E less than or equal to G, E less than or equal to G. So B automatically less than or equal to G, D is less than or equal to G. Here less than or equal to is relation. So in that way you can understand upper bounds of any element or upper bounds of any set S. Now we'll see lower bound of set S. So lower bound of set S is a set, which is nothing but set of lower bounds of set S. But what is lower bound? Example, an element X belongs to your lower bound. Then what's the property of it? I am explaining you. If X is a lower bound of set S, that means X belongs to, that is what my assumption. Let's say X belongs to lower bounds of set S. Then according to the definition, X should belongs to poset. Second one, for every Y belongs to your set which you are talking about, for which you are calculating lower bound, what should happen is X is related to Y. So let me pictorially represent it. So that means whenever you say X is one of the lower bound of set S, then X should be related to Y for every Y belongs to your set S. Example, this is your set S, okay, like Y1, Y2, Y3, so on. So X should be related to Y. Less than or equal to means relation. That means X is related to Y, X is related to Y2, X is related to Y3, so on. That is called lower bound concept. So here X is a lower bound. Now identify this kind of structure in the picture so that easily we can calculate lower bound of any set S. Okay. So again there can be multiple lower bounds. Example, there is one more element like A. If A is related to X, according to transitive property, A is also related to Y1, A is related to Y2, A is related to Y3. So that is a property of a lower bound of set S. So A is also a lower bound of this set S. Understand? We'll see with some examples. Yeah, see this one. A, B, C, D. Let me take A comma B comma, let's say A comma B. What are the lower bounds of A comma B? We'll see. So whatever may be the lower bound, its property is it should be less than or equal to A, less than or equal to B. That's it. That is what lower bound. So here less than or equal to means relation, right? So can you show any element which is related to A, related to B? For that, to have a relation from something to A, there should be a path from X to A. But from any other element there is no path to A, isn't it? So the only possibility is A. Let's try A. A is related to A, correct? A is related to B, correct? Absolutely. That's why A is a lower bound of A comma B. Perfect. But B is not lower bound, okay? The reason, if B is a lower bound of A comma B, B should be related to A, B should be related to B. Since B is not related to A, B is not related to A, this is absolutely false, right? So for A comma B, B is not lower bound. We'll see one more example. Let's take E comma G comma F, okay, for this one. So suggest one lower bound for EGF. I guess D. Let me just guess. I know that it is wrong, but I'm just trying to say that D is not a lower bound. If really D is lower bound, D should be related to E, D should be related to G, D should be related to F. Yeah. So D is related to E, absolutely right. D is related to G, absolutely right. There is a path, you see, right? But D is related to F is wrong, right? That's why this is not a lower bound. So what could be the lower bound for this problem then? I think A. A is the only lower bound. You can check it out. So A less than or equal to E, A less than or equal to G, A less than or equal to F. Only A satisfies this property. So A is a lower bound. Okay. Now, what if you have only single element in your set S? Example, set S equal to G. What are the lower bounds of G? Simple. If anything is lower bound, it should be related to every element of S. Since there is only one element, then your element should be related to G. So tell me one element which is related to G, G itself, isn't it? That's why G less than or equal to G. Correct. So here it is relation, right? G is related to G. Absolutely right. So G is one of the lower bound. Similarly, already G is connected to E like this, correct? So if G is lower bound, something is connected to G like this, then that will become lower bounds in that way. So E, D, B, C, A, F, everything is connected to G. So they all will become lower bounds, right? So example, why A is lower bound I will tell you so that you can understand remaining things. A is related to G or not is the question, okay? Yes, that's why A is lower bound of G. Understand? So this is a way you can understand upper bounds and lower bounds for any set S. Let's see two more important things to learn about lattices. One is least upper bound and greatest lower bound. Okay. So let's begin with the least upper bound of set S. Already we know what is upper bound, isn't it? And you know what is minimum element. Then if you know these two things, we can understand least upper bound easily. So least upper bound of any set is nothing but minimum element among all the upper bounds of set S. That's it. Similarly, greatest lower bound of set S is nothing but maximum element among all the lower bounds of set S. Greatest means maximum, least means minimum. Okay. So we'll see with examples how to compute LUB and GLB. Often we denote this least upper bound with an operator called OR and greatest lower bound of any set with operator AND. Okay. So from now onwards, let's make them operators. Greatest lower bound and least upper bounds are operators. Okay, this is OR operator, this is AND operator. Let's try to find out least upper bound of this hash diagram. Let's take an example for B comma C. What is least upper bound of B comma C? Something is least upper bound for anything, then we know the definition. First of all, we have to compute upper bounds, right? What is upper bounds of B comma C? Tell me one upper bound of B comma C. So upper bounds of B comma C, one is E. Is it true? No, right? So what's the problem with E? B is related to E, but C is not related to E. That's why E is not upper bound. There is only one element which is related to B comma C. What is it? B to F, C to F. That's why F is one of the upper bound. There is no other upper bound. That's why. So the collection of all the upper bounds, if I do, then I get only single element. Now, what is least upper bound is we have to identify minimum element among the set which is given, which is nothing but upper bounds. Since there is single element, minimum element among single element is that element itself, right? So F is the answer. Now, we'll see what is least upper bound of A comma B. Okay, I am calculating least upper bound of set A comma B. For that, step number 1, list out all the upper bounds of A comma B first. Upper bounds of A comma B are nothing but elements which are related to A, related to B. Is it not E? Yes. E is related to, that means A is related to E, B is related to A. Okay, if you don't understand it, so definitely you should revise the concepts of lower bound and upper bound. Okay, so what I do is, before watching this lecture, so take lot of examples and compute minimal elements, maximal elements, upper bounds, lower bounds before coming to this lecture. Okay, without knowing them clearly, so it will be very difficult for you to understand it. Okay, now least upper bound of A comma B is, one is E. Now F is also, you see, B is related to F, A is related to F. Now D 2. Why D? Is it true? No, I think, right? B is not related to D, but A is related to D. That's why. So D is not upper bound. Okay, don't add it. Anything else? So I think only E comma F are upper bounds of A comma B, right? So add it. Now out of them, what is least? That means we have to compute minimum. Tell me minimum element in E comma F. Already we have studied what is minimum element. Okay, apply it. Minimum of EF is, we know that E. Right, answer is E. In that way we can compute least upper bound for any set. Let's see some examples of greatest lower bound. Okay, so greatest lower bound of set S, we know that it is maximum of lower bounds of S, right? So example, greatest lower bound of set ABC, we'll try to do it. Okay, for that we have to compute lower bounds first, right? What is lower bound of ABC? Lower bound of ABC is a set of all the lower bounds, right? Tell me one lower bound of ABC. I think that is E, right? Why it is lower bound? Because E is related to A, see, E is related to B, E is related to C. This is one lower bound. Similarly, you collect all the lower bounds, that will become lower bound set. So I think F is not lower bound. If F is lower bound, F should be related to A. Yes. F should be related to B, yes, but F is not related to C, isn't it? That's why F cannot be lower bound. In that way you can realize that there is no other lower bound. Now apply maximum, since it is greatest, maximum among all the elements you have, which is only one element, that element itself will become maximum, isn't it? So that's why E is the greatest lower bound for A, B, C. Let us take one more example. Greatest lower bound of a set B comma F. Let's try that. For that, lower bounds of B comma F first. Tell me what are all the lower bounds of B comma F? Lower bounds of B comma F should be elements which are related to F, related to B. Since F is related to B and F is related to itself, then F will become one lower bound, right? Anything else? Since E is related to F and F is related to B comma F, so E is automatically related to B comma F. That's why E is one more lower bound. So these are all lower bounds of set BF. Anything else? I think only E comma F. D cannot be the answer because D is not related to F or B. So anything else is, nothing is related to B comma F other than F comma E. Now we need maximum. Maximum of F comma E. So there is only one element which can be maximum, we know that definitely F, right? So if you don't understand this concept, definitely you have a problem with maximum elements, minimum elements and lower bounds and upper bounds. Better you clarify them with previous videos, and after that you please come to this session. Okay, so this is about greatest lower bound of this problem. Let me take one more example by adding this edge here. I construct a different hash diagram. In that one again we'll see what is lower bound, what is upper bound, and what is greatest lower bound. So greatest lower bound of, let's say, B comma C. We'll try to compute. So greatest lower bounds of B comma C for this problem is, first we compute lower bounds of B comma C, then maximum, right? Lower bounds of BC. So I think D is not lower bound, because is it lower bound? Yes. Since D is related to B, D is related to C. Yes, D. Now F is related to C, F is related to B. Anything else? Since E is connected to them, E is also. Right? We got 3 lower bounds for BC. But what is maximum element? Maximum of DFE. Try to identify. So maximum among DFE. See the picture. In this DFE, is there any maximum element? No. Maximum element is an element which is greater than or equal to every element. Otherwise, all the elements should be related to that element. Out of them, F cannot be maximum, because F is not, all the elements are not related to F. You see, A is related to F, but D is not related to F. Similarly, D is not maximum because F is not related to D. Maximum element should be related by every other element. Did you remember that? That's why. Without understanding maximum concept, you can't understand it. So you realize that there is no maximum element here. So that means GLB is empty. Okay. For this picture, we'll see least upper bound of some set. Let me take F comma D, and I would like to compute least upper bound one more time. For that we need upper bounds first. Upper bounds of F comma D. Upper bound is an element which is related to F. That means F is related to that element, D is related to that element. So is there an element which is related by F and D? Yes, C and B and A. See, F to C, D to C. C is upper bound. For FD, F is related to B, D is related to B. That's why one is B, one is C, one is A. So these are all upper bounds, isn't it? Now, for all these upper bounds, what is least? Least of ABC is nothing, like previous example, right? So that's why there is no least upper bound for this set. Understand? So let me finish up this concept by last example, that is, what is least upper bound of E comma F? Second one, what is greatest lower bound of A comma B? Let's try these two. So least upper bounds of E comma F. Any element is upper bound of, first of all, let's compute upper bounds of E comma F. Okay, an element is called upper bound if it is related by E, related by F. So it should be related by E and F at a time. So B, correct? See, F relates B, E relates B. So B is an upper bound. Let me add slowly for E comma F. See, C is also, F is related to C and E is related to C, right? But not D, because F is not related to D. So I can see A also, right? So B, C, A. So for E comma F, upper bounds are B, C, A, but one more thing. What is that? F. F is also related to F. Why F is in upper bounds is, see, E is related to F. Yes or no? Yes. F is related to F. Yes or no? Yes. That's why F is also an upper bound. So we have 4 upper bounds. Out of them, we have to compute least. What is least in BCFA? See the picture. BCFA. BCFA. And that, what is least element? Okay, I am showing them. B, C, F, A. Okay. In these 4, F is minimum element, isn't it? Because F is related to C, F is related to B, F is related to A, F is related to itself. So F is minimum. Perfect. Now we'll compute greatest lower bounds of A comma B. So for this problem is answer F. Now we'll see greatest lower bound of A comma B. First collect all the lower bounds of A comma B. Lower bounds of A comma B is First, F, because F is related to B, F is related to A. That's a concept of lower bound. So F. Next, D is related to B. We have to compute lower bounds of AB, right? Yes, D is related to B. Since B is related to A, automatically D is related to A, isn't it? So D. Anything else? E. Since E is related to D, then D is already lower bound, then E would become lower bound. So what about any other element? We have now F, D, E. So we are targeting A comma B, isn't it? For A comma B, F, D, E. Perfect. C is not right answer because C is not related to B, correct? So are you seeing any other element for lower bounds of AB? Yes, you always miss this point, right? B is related to B, B is related to A, then B should be lower bound, isn't it? So F, D, E, B are the collection. Out of them, we have to compute greatest. What is greatest among F, D, E, B? The greatest is B, isn't it? So B is the greatest element or maximum. So if you are comfortable with computing maximum, it's not a big deal to say that B is the maximum element among B, F, D, E. Okay. So in that way, easily we can compute least upper bounds and greatest lower bound for any set, not an issue. But before attending this lecture, my suggestion is take lot of diagrams and compute minimal, maximal, minimum, maximum. Then only you can do it very easily. Okay. In partial order relations, often we use this all symbols. R, of course you know what is R, and less than or equal to, greater than or equal to, less than, greater than. Okay. Please don't get confused with ordinary mathematics symbol less than or equal to, greater than, less than. Okay. They are quite different from this. Here our intention is we want to use this R. That means this is main objective for us, relation. So we use the less than or equal to just notate or use a different symbol for R. That's it. Okay. So R is generally symbol for relation. Less than or equal to is the symbol for partial order relation. Okay. So that's it. But it's not. It may not be mathematical symbol less than or equal to. Okay. So with this idea, I would like to mention what is greater than or equal to, less than, and greater than everything. Start. So what you do is, first you learn what is less than or equal to, less than, greater than or equal to. After that, try to take lot of this kind of pictures which are hash diagrams and try to apply these concepts. Okay, ready? First, I start with R. R means whenever an element A is related to B in a relation, we say that A comma B belongs to R. Correct or not? Otherwise, we say A is related to B. Whenever I say A is related to B, then A comma B belongs to R. Of course, you know it, but let me brush up it. But B comma A is not belongs to R. Okay. Now, when we construct hash diagram, for every A comma B belongs to R, we add an edge. After that, we remove self loops and parallel edges or transitive edges, isn't it? So, if I remove transitive edges and self loops, whatever the remaining edges will have, that we see in hash diagram. But relation wise, still they hold good. Example, there is a self loop actually, right? That means A is related to A, but I removed the this edge from the picture. It doesn't mean that we are removing the relation, right? So still A is related to A. There is no edge from A to A in the picture. Similarly, D to C, C to B, then there was an edge from D to B, which we have erased it, isn't it? But it doesn't mean that we removed that symbol from, or that relation from D to B. We are not removing the relation from D to B. Remember it. Okay. With that concept, let me explain what is R with this picture. In picture, how to see R? D is related to E. Yes, because there is direct edge. Remember, whenever there is a direct edge or a path, because path represents transitive edge. Okay. Otherwise, self loop. Everything is R. D is related to E. Yes. Okay. So D is related to E is correct. True. I am writing true for T. I mean T for true and F for false. Okay. D is related to B. Correct. There is a path. True. And G is related to A. Absolutely right. True. D is related to A. there is a path from D to A, correct, in that way. So I can say that these are all true. D is related to D. Yes, there was a self loop I removed, but still relation holds. That's why it is true. So this is about R. Now we'll come to less than or equal to. Before that, I would like to mention one more thing, B versus G. So B is related to G. Is it true? So is there any path from B to G? I can't see because directions are important. Let me put directions too. Okay. There is no edge or there is no path from B to G. It means there is no relation from B to G in the original relation. That's why it is false. Similarly, G is not related to B since there is no path from G to B. Understand? Now, what about D to G? D is related to G. Absolutely wrong. If I start at D, I can't reach G through these directed edges. That's why it is false. Okay. This is about R. Now we'll see what is less than or equal to. Less than or equal to is simply represents R. So wherever I keep R, I also can keep less than or equal to. So R is a symbol for relation, less than or equal to also a symbol for relation, but generally we use less than or equal to represent partial order relation. Okay. So still everything is correct. That means D less than or equal to E. Whenever this question is asked, then you just interpret it like R. D is related to E or not? Yes, true. That's why, so everything is correct. D less than or equal to B correct. G less than or equal to A correct. So D less than or equal to A correct. Everywhere I can write less than or equal to. D less than or equal to everything. So all are like true, 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 true. And D is less than or equal to G is false. Okay, in that way you can understand about less than or equal to. So it is B, right? Okay. B less than or equal to G is false since R and less than or equal to are same. Now we'll see what is greater than or equal to. It's very simple. Whenever you want to say A less than or equal to B, then that is equivalent to B greater than or equal to A. Both are same. Greater than or equal to is not a new symbol. Whenever A is related to B, we say that A less than or equal to B. Whenever that is true, you simply say B greater than or equal to A. See now. Whenever A is related to B, then B greater than or equal to A. B greater than or equal to A less than or equal to B. Understand? So greater than or equal to is not a new symbol. We can derive it from less than or equal to. First check less than or equal to. After that, do the reverse. Like that means, example someone asks B greater than or equal to A. Then see like this. A less than or equal to B or A is related to B. A is related to B, not B related to A. Don't check that. Okay. So let's try to check that things here. C greater than or equal to D. If you want to know, so see, D is related to A. This question is like D is related to C. D is related to C. Yes, that's why C greater than or equal to D is true. Now, example D versus A. D is greater than or equal to A. For that, A should be less than or equal to D. But A is not less than or equal to D, isn't it? That's why this is false. So saying D greater than or equal to A is absolutely right, false. What about C comma A? Can I say A greater than or equal to C? Can we say C less than or equal to A? Absolutely, since C is related to A. When C is related to A, saying A greater than or equal to C is true. In that way we can understand. Okay. Now, like here you see E greater than or equal to D, B greater than or equal to D, A greater than or equal to G, everything is correct. This is about greater than or equal to. Keep practice about these symbols. Now less than. How less than is different from less than or equal to, I will tell you. Very simple. Whenever A and B are related like this, A is related to B and A not equal to B. That means there are two different symbols and which are related from A to B, then we say A less than B. Okay, remember it. It's like A less than or equal to B, but they should be different symbols. So whenever you want to check the relation between, less than relation between two elements, please ensure they are not equal and there is a relation between them. Let's see what is A greater than B. For that, B should be related to A. Okay, B should be related to A. but again A not equal to B, then we say B greater than A. Understand? So if you want to say B greater than A, B should be related to A, sorry, A should be related to B, but A not equal to B. So same thing. Okay, so what's the difference between less than and greater than? Whenever A is related to B but which are not equal, then A less than B. Now whenever A less than B, automatically for same pair of elements B is greater than A. Saying A less than B and saying B greater than A are same. Okay, they are not different. So the relation between less than and greater than is very easy to understand. When A less than B, simply say B greater than A. So how to define B greater than A is, again A is related to B, that's why A is related to B but A not equal to B. That's it. You understand? So this is about greater than. We'll see some examples how to check greater than between two elements. Example F comma A. The question is F greater than A. If you want to know, ask a reverse question, G less than F and G, right here, see. So let's try with A first, F comma A. Okay, after that we'll come to FG. F greater than A is the question. For that you ask a reverse question, A less than F? No, right? So A less than F means A is related to F? No, that's why it's false. Then this is false. Next question. What about A greater than F? Yeah, A and F are two different elements, then it might be true. First of all, they should be different elements. Yes. Second one, F should be related to A. This should happen. F is related to A. Yeah, F is related to A. F is related to A and F and A are different. That's why A greater than F. Understand? In that way, we can talk about greater than, less than, and we can understand about them. Okay. Let's see a technique to compute least upper bound and greatest lower bound. Sometimes it will be very difficult to find out LUB and GLB in a picture. So for that people, so let me give you one small technique or interpretation. So if you follow this interpretation or imagination, then easily we can compute GLB and LUB for any picture. So what is that idea? We'll see. So we know that LUB is denoted by R and GLB is denoted by AND, right? So example, whenever you want to compute LUB of H comma A, okay, then what is LUB? It is nothing but least upper bound, isn't it? So for that we have to compute upper bounds. To compute upper bounds, use this imagination. Go to H point, write some color, example red color. Okay, imagine that there is a red color liquid here, and go to A and write some a different color of liquid, let's say green. Then since it is upper bonds, imagine flow is, it's all about flow. Okay, so this picture hash diagram can be imagined as a flow from generally top to bottom. Okay, now for upper bonds, imagine a flow from bottom to top, sorry, yes, bottom to top. Then this is H, this is A. Okay, if this red color liquid and green color liquid, if they go upwards, what happens? There is no other point. After this point there is no other point to reach. Then red color will remain here and green color will remain here. So there is no joining point, isn't it? So that's why, so I say that there is no common upper bond for red and green. If and all if there is a upper bond, it looks like this. From H2 there will be a path to one point. For the same point there will be a path from A, but that won't happen here, isn't it? So that's why upper bonds of H comma A is nothing, there is no common point. Then let's say empty, and least upper bond of empty is nothing but empty, right? Least means minimum. Minimum of nothing is nothing. Now let's take one more example. This time we'll take E comma F comma G. So what is LUB of E comma F comma G? Further take three colors. one at E red, F let's say green, and one more is yellow. Okay, imagine again colors are flowing from bottom to top. Let's say from F, if some color goes like this, then from this green color goes in two directions like this. Now yellow color goes like this, right? It goes this side. Even red color, green color also goes in this direction, correct? Wherever there is a pipe, they flow. With this idea, I can say that you get a common color only at this point, isn't it? Let's see, remove this one, red, okay, this green. So with respect to red, green, yellow, then what is the common point where you get red, green, yellow mix? The only point I can see is A, isn't it? So this is a A. But imagine flow is going upwards. That's why you don't get mix at D, isn't it? So, but what about H? You can get red here and you can get green, but you can't get yellow because yellow won't flow from G to F, isn't it? That's why the only common point is A, right? I will show you that. So green color is flowing like this, red color is flowing like this, and yellow color is flowing like this. This is the only point where you get all three colors. Then I can say that is upper bond. So upper bond is A, and least among all the upper bonds is A, right? Since minimum of single element is A. Upper bond is A, minimum element is A. Right? In that way you can compute least upper bonds. Let's see greatest lower bond for the same concept. Okay. Otherwise, let me take this picture and I will teach you what is greatest lower bond, how to interpret it. Example, let's say you want to find out, greatest lower bond of B comma C. Okay, for B comma C. Imagine that this is red color point, origin of red color. This is origin of green color. Okay. Now this time, since it is a lower bond concept, imagine flow is coming from up to bottom like this. So when flow goes like this, then what are the common points where you get red color and green color? See, here you see red color and green color flowing. Yes. So this is one point, and since after that the mix comes to F, but after F it won't go to D. The reason, directions are important from top to bottom because we are studying now lower bonds. So one common point is F for red and green, and one common point is E. One common point is D. You see green color is coming like this, red color is coming there. So finally D, E, F are all common points where you get mix of the colors, isn't it? Then out of them we have to compute greatest. Okay, so that means maximum of DEF. So just imagine what is DEF here. DEF, what is maximum element of any set? That is an element which is greater than every element, right? So there is no element which is greater than or equal to DEF all, right? We know that. So when you have this kind of structure, so minimum is F, but there is no maximum. That's why nothing. So if you don't understand that max of DEF is empty, you have a problem with identifying maximum element. Please go through video lectures where I taught you maximum element. Okay, then only you can understand this. So this, using this perception, quickly you can find out upper bonds and lower bonds, right? Let's see another topic in hash diagrams, that is comparable elements in hash diagram. So comparable elements are elements, let's say A comma B. The concept is like this. Whenever A is related to B or B is related to A, that means we say that there is a relation between A and B, then A and B will become comparable elements. Okay, so I am writing the definition. A and B are comparable if and only if A is related to B or B is related to A. Okay, at least one direction should hold. Sometimes what happens, neither A is related to B nor B is related to A. In that case, we say that they are incomparable elements. There are two things. One is comparability, second one incomparability. If elements are not comparable, then they are incomparable. Example, See this picture, D comma E. Neither D is related to E is related to D, isn't it? That's why D comma E are incomparable. Take F comma A. So there is a relation from F to A, we know that, isn't it? So F is related to A. So F and A are comparable. Okay. Similarly, B, C are incomparable. B comma E are comparable. So it's all about how you understand R, whether you can check A is related to B or not. Okay. If A is related to B or B is related to A, simply say that elements are comparable, otherwise they are incomparable. Okay. Incomparable elements always will have this kind of structure, like they will be 2 points where there is no path between them. That's it, so simple.